Hello there, and welcome to this video lecture on heat integration, pinch technology, minimum number of utilities, minimum number of heat exchangers method, part 4, constructing a cascade diagram. Reviewing our 6 steps in heat integration, we've optimized our process. We chose a 10-degree minimum approach temperature. We've laid out our hot and cold streams, and we've constructed a temperature interval diagram. Our next step is to construct a cascade diagram, and this is to determine our pinch points. You may be wondering what a pinch is, and it occurs when heat can no longer be transferred between streams, and a hot utility such as steam or natural gas must be used. In other words, we've run out of heat to heat up a stream that needs to be heated, and we have to use a hot utility. Looking at our temperature interval diagram that we made in the previous lecture, we see that we have our Qs for blocks A, B, C, and D. And this information is really important for constructing a cascade diagram. To construct our cascade diagram, we start off with 2 blocks on the left and right sides. These are the hot utility and cold utility. The hot utility can be thought of as steam or any other heating utility, and we will derive heat from this block when necessary. The cold utility is cooling water or refrigerant, so when we need to cool a stream, we will use the cold utility. And so we first start by setting up our blocks that we determined from the previous lecture. Blocks A, B, C, and D, their Q values are shown in the squares here. And the cascade diagram gets its name because we will be cascading heat down from one block to another. So we'll start at the top. We start with block A. Block A has 300 kilowatts of heat to give, so it sends 300 kilowatts of heat to block B. Block B takes 50 kilowatts of heat because it needs 50 kilowatts of heat, so it can send 250 kilowatts of heat to block C. Block C, however, needs 350 kilowatts of heat, so we need to supplement the 250 kilowatts with 100 kilowatts from a heating utility. What this means is that we have no heat to give to the final block, block D, and this therefore represents a pinch point. Block D has 50 kilowatts of heat to give, but no block to send it down to. So that means we dispose of it by using a cold utility. I notice that students sometimes have difficulty understanding cascade diagrams and how to cascade heat down and when to use hot utility and cold utilities. So I'm presenting 2 examples to you. This is the first one. It has blocks A through F. And if you'd like to pause the recording and test your knowledge so far of cascade diagrams, see if you know when you need to use the hot utility, when you need to use the cold utility, and where the pinch points are. We start every cascade diagram at the top. We see block A has 400 kilowatts of heat to give. So we send 400 kilowatts to block B. Block B has 900 kilowatts of heat, so we can combine 400 and 900 to send 1300 kilowatts of heat to block C. Block C, however, requires 1400 kilowatts of heat, so we need to supplement with the hot utility, and this means that we have reached a pinch point. Block D does have 1200 kilowatts of heat to send to block E. It combines with E's 400 kilowatts to send 1600 kilowatts to block F. Block F has 300 kilowatts of heat. This means that we have an excess of 1900 kilowatts of heat that we need to dispose of using the cold utility. This is the second example just for practice. I've created more blocks with this one, and you might notice that I've also shortened the blocks so that I can fit more of them on the screen. If you'd like to pause the recording here, see if you know when you need to use the hot utility, when do you need to use the cold utility, and when there are pinch points. We start with block A. Block A starts off with a heat deficit. This means that we have to send 1,000 kilowatts of heat to block A, and we've already encountered a pinch point because there is no heat to send from block A to block B. Block B also requires 200 kilowatts of heat. This is another pinch point that we've encountered here. We have no heat to send between block B and block C. Block C is the same story. We require 400 kilowatts of heat to be sent to block C. There is no heat to send to block D. However, block D does have heat to send to block E, 600 kilowatts. Block E combines with the 600 kilowatts to send 700 kilowatts to block F. Block F requires 1,000 kilowatts. So we need to supplement this with 300 kilowatts of heat. This is now our fourth pinch point. We have no heat to send between F and G. And G requires heat, 500 kilowatts, so we send 500 kilowatts to block G, and then we have our fifth pinch point. Block H has 1,000 kilowatts of heat to give to block I. However, block I requires 2,200 kilowatts of heat, so we supplement with 1,200 kilowatts of heat for block I. Notice we don't have a pinch point under block I, simply because there's no block under it. So you might have been wondering what the purpose of all of this is. And the purpose is that we need to design a set of heat exchangers above the pinch and a set of heat exchangers below the pinch. So this is our cascade diagram, again from before. We have one pinch point. We have to design one set of heat exchangers above the pinch, one set of heat exchangers below the pinch, and there are different rules that we need to follow above the pinch and below the pinch. So we've determined some really important information here. We need to design one set of heat exchangers for blocks A, B, and C. We need to design another set of heat exchangers for block D. Block D is below the pinch. We also need to provide 100 kilowatts of heat to blocks A, B, and C, somewhere in blocks A, B, and C. And we need to dispose of 50 kilowatts of heat from block D. So this is giving us some very, very important information in terms of how we will lay out our heat exchangers in the next step.